Hi, this video will cover section 4.4, examples 6 through 11. So we're going to continue solving equations, and for this equation here, we have an exponential one, but we're going to be using some logarithmic properties to solve it. So what do we need to solve for? Well, here we have two letters, E and X, but the only unknown variable that we have to solve for is X. That's what we need to find a numerical value for. The letter E is representing the number, Euler's number, which is approximately 2.71. And you do have a calculator for that, so don't use the approximation, use the button for E. So in this case, we see that the number 3 is multiplying e to the power x squared. So let's think about moving things out of the way by moving them across the equal sign and doing the inverse operation. So the first thing we will do is take that 3 across. And so since it is multiplying on the left side, on the right side is going to be doing the inverse, dividing. And since this is an easy division, we could divide it, but if it wasn't, I will just suggest to put it in parentheses. It's 200. So if we had something like a to the power x is equal to, let's say, 200. The way we will convert it to a logarithmic expression will be by, first you write log, then the base of the exponential will become the base of the is equal to this exponent here, x. And so we're going to use that same idea to change from exponential to logarithmic. So if I do that, it will be log base e of 200 is equal to this exponent x squared. Now we do have a special prefix for log base e, and that is ln. So the ln of natural log of 200 is equal to x squared. Now here, to get rid of a square, the inverse operation will be to take the square root. So we will do that on both sides. Since the square root and the square are inverse operations of each other, it will cancel. You get x. And then here, we're going to find the square root of the natural log of 200. So you could enter all of that on the square root function of your calculator, or you could also enter it this way, natural log of 200. You got to open this parentheses and then close it again. And then the exponent symbol, and then you can enter 1/2 or 1 divided by 2. So that will give us the solution for x. And so x will be approximately, I need to find that with my calculator. So that will be the square root of the natural log of 200 it will be 2.302 if we were to round to 3 decimal places. Now the next example, example 7, it is an application. In chapter 5, we're going to discuss more applications from finance and other science fields. And the one that we have here is a logarithmic function, which is representing the number of non-farm jobs in millions added to the US economy quarter by each quarter of the year, like every 3 months, and that could be approximated by the function. So it says here that x equals 1 corresponds to the first quarter of the year 2014. So x, the input, here we'll have x equals 1, x equals 2, x equals 3, and so this is the year, all of it is the year 2019. Oh, sorry, 2014. So this will be the first quarter, the second quarter, the third quarter, and the fourth quarter of the year 2014. That's what this is telling us. Now the output, the function value, or the y value, remember those two, we use them for the same purpose to represent the output. It's going to be giving us the number of non-farm jobs in millions. So now let's read the question. Find the first full quarter. So in this case, we're looking for x. We're not looking for y, we're looking for x, in which the number of jobs added to the economy exceeded 16 million. So we want that to be more than 16 million. And so what we're going to be doing is we know that this function is increasing, and so we want to know when it will be exactly at 16 million, and perhaps we will have to round up because we want to know when it exceeded the 16 million. So what I'm going to do is substitute f of x, or the output, or the y value. So this is telling me if y is equal to 16, or f of x is equal to 16, find x. So that's what we're going to do with the function. Instead of f of x, we're going to substitute that with 16. So 16 is equal to 12.1 plus 2.03 natural log of x. And of course, we're solving for x. So first thing we do is take this positive 12.1 across the equal sign. So instead of adding, it will be subtracting. And then here we will have 2.03 times, because there's no sign in between natural log and 2.03, log of x. So if we subtract those two numbers, 16 minus 12.1, we will get 3.9. And here we have 2.03 natural log x. You know the 2.03 is multiplying to the natural log, and so we're going to take it across the equal sign, and it will be dividing. Okay, so we're almost done. We're just going to leave that in parentheses. We're not actually going to divide it yet. Now, remember that if you have natural log, you're talking about a logarithm of base e. And so if I convert that into an exponential expression, it will result in e to the power, and it will be everything that we have in parentheses here. So to the power 3.9 divided by 2.03 is equal to x. And so now what you need to enter on your calculator will be, well, if you have 84, you need to use the second key. And then you need to use the LM key so that you are actually, with these two keys, you're actually calling e to the power x. Then if the caret symbol opens automatically, good for you. If not, go ahead and press it. And then in parentheses, you want to enter the whole exponent 3.9 divided by 2.03 and then close your parentheses. So I'm going to go ahead and find that on my calculator. You should do the same thing so that you can check your answer. So e to the power x, and then I will have 3.9 divided by 2.03. And that will give me from here. So I'm going to get that x is equal to 6.83 if I was to round to 2 decimal places or to the nearest hundredth. So that will be the solution. Now, if my math lab was to ask you for the exact solution, this will be the exact solution. E to that power, just like that, without rounding. Approximate, it will be, the approximated solution will be 6.83. Okay, so let's move on to the next problem. And this talks about digital groceries. And for this one, think about like Instacart or I don't know, Blue Apron, things like that. The amount of money that US consumers spend online for food in billions of dollars can be approximated by this function here, where x equals 11. Oh, actually, I do need to go back to this problem. Sorry, because that was not the answer. I believe we got something like x equals 6.829. And so we had established how the first quarter of the year 2014 was x equals 1. And then x equals 2 was the second quarter. This was for the year 2019. Then we had x equals 3 was the third quarter, and x equals 4 was the fourth quarter. So if we go, not 2019, I don't know why I keep saying that, it's 2014. That is what the problem states right here. And so if we move on to the next year, which will be 2015, this will be the first quarter of 2015 will be represented by x equals not 4 but 5, then x equals 7, and then x equals 8. Now the answer that we got was x equals 6.8829. So we're going to have to round it to x equals 7 because first of all, we're talking about integers here, but also they're like the quarters of the year. And also because we want the first quarter when it exceeded 16 million. And so it makes sense that we round up. And so x equals 7 corresponds to the third quarter of the year 2015. X equals 5 is the first quarter, x equals 6 is the second quarter, so then x equals 7 is the third quarter of the year 2015. And so the answer will be that, the third quarter of 2015. Now going back to the other problem, example 8. And so we have here that x equals 11 corresponds to the year 2011. So now x is representing the year, and y, or f of x, the output, is going to be representing the amount of money spent in online groceries. So the question here is, assuming that the model remains accurate, determine the first full year, so we're looking for x, in which online grocery sales exceed 50 billion. So they're giving us y, the output, or we could say f of x equals 50. Again, we're talking about exceed, so we're going to be looking for something greater than 50. However, we're just going to substitute into this function, we're going to substitute f of x. So I'm just going to write the function again. F of x is equal to 0.174 times 1.318 to the power x. So we substitute f of x with 50. And here we have 0.174 times 1.318 to the power x. Then from here, this quantity is multiplying the base, 1.318. So it makes sense that if I take it across the equal sign, it will be doing the inverse operation, so it will be dividing. So 0.174. And that will equal 1.318 to the power x. We're not going to divide this, we're just going to leave it like that in parentheses. And so now we're going to take the exponent across. I'm sorry, no. I'm getting ahead. We're going to take the natural log on both sides. So we take the natural log on this side again. As well. And now this exponent, the x, now we use that power property. So the exponent becomes the coefficient. So now what we need to do, you could see how x is being multiplied by this expression. And so the right thing to do is to take it across. First, I'm going to write what I already had on the left. Natural log of 50 divided by 1.74. And then that divided by this whole thing. Natural log of 1.318. Okay, so the way you will enter this on your calculator, natural log of 50 divided by 0.174. Close parentheses, then you have to press the division key again, and then natural log of 1.318, and you close parentheses. And so if we enter all of that on the calculator, which I'm about to do, and that will give me that X is approximately 20.5. Now remember, if we were to change that into a year, X equals 11 was corresponding to the year 2011. So since we got X equals 20.5, we're going to go ahead and round that up to X equals 21. And so that will correspond to the year 2021. And so that will be the year when the cells will exceed 50 billion. Now for the next problem, this problem talks about carbon dating. And for this, we use half-life. Carbon-14, which is an isotope of carbon, it has a very large half-life, meaning that it will take those many years, 5,730 years, for a certain amount of carbon to become half of it. So if let's say that we start with 100 grams of carbon-14, so after those many years, you will get 50 grams. Now, you have 50 grams, and then after another 5,730 years, you will get half of that. It doesn't mean that it will go to 0, it'll just be half of 50, so it will be 25 grams. Now, after another 5,730 years, those 25 grams will become half of that, so it will be 12.5 grams. And in another 5,730 years, those 12.5 grams will become half of that, so it will be 6.25, and so on. So as you can see here, we already went over 20,000 years. So that's the reason why people can determine the age of very old artifacts or human remains, or even dinosaur skeletons or fossils. So the problem talks about the King Arthur round table where he used to gather with all his knights. And when this table was found, they did not know if it could possibly be a table that belonged to King Arthur. And so what they knew is that, based on chemical analysis, that the amount of carbon-14 compared to a table of the same material, which I'm assuming is wood. Oh, actually, it says here, wooden table. So it had lost 9% of what a table should have. So let's say 100% of carbon-14, and when the table was found, it had lost 9%. So 100 minus 9 will give us 91%. So what happened here is that the original amount when the table was found, let's say if we're going to use t for time, at time 0, the amount remaining, which is y sub 0, y value at time 0, was 91%. We're going to convert percent to decimal, and so we need to divide by 100, so that will be 0.91. So now what we're going to use is one of these two equations, either one. So we're going to say, and that is to solve this type of problems, f of t is equal to y sub 0 times 1/2 to the power t over h. So what we're going to do here, and actually I want to correct myself. Okay, so this is very wrong. Okay, so at time 0, like when the table was created, it had this much of carbon-14. Now, at t equals question mark, because that's actually what we're looking for, the amount of carbon-14 was 91% of the original. And so that's why I'm going to write 0.91 y sub 0. Like if the amount remaining was 50%, I would have said 0.50 times y sub 0. And so why do I do this? Well, because we are not dealing with numbers. We don't know how many grams or milligrams of carbon-14 we're talking about. All we know is that we had 91% of the original amount. And so because of that, we're going to turn this f of t, the future amount or the amount at which it was found, it was 0.91 times y sub 0. Now, on this right side, we have equals y sub 0 times 1/2. And now what I'm going to use is place t here, which is what we're looking for. And h is actually going to be the half-life, which is 5,730. So now from there, we're going to solve the equation. And what first thing we could see is that y sub 0 is multiplying all this stuff here. And so I'm going to take it to the other side. And what I'm going to be doing is dividing by y sub 0. And you know I don't like to write it this way, but I'm just going to do it so you can visualize it. We do that because we want to cancel y0 on the right side. Now, what happens on the left side? Well, also y sub 0 gets canceled. So now all we have left is 0.91 is equal to 1/2. I can use, let's just keep using 1/2 to the power t divided by 5,730. So from here, what we can do is take the natural log on both sides. And here, let's just write, instead of 1/2, let's write 0.5. And here we have t to the power 5,730. So what I'm going to do is use the power rule. So I'm going to take that exponent and place it here as the coefficient. So now this is natural log of 0.91 is equal to t over 5,730 times the natural log of 0.5. And so that natural log of 0.5, I can actually put it right here because it's multiplying. So now one thing we can do is take this expression, multiply it by 5,730, and then divide it by natural log of 5. Or we could do that all at once by doing the following. And I don't have space for it, so I'm going to have to make some. Oh, no, I didn't want to do that. Okay, so I believe we had something like 0.91 equal to t over 5,730. And then here we had natural log of 0.5. Oh, and this was natural log as well. Okay, so what I was saying was this is dividing, so I can take it across. And now it will be multiplying. Natural log of 0.5 is multiplying to the t. So if I take it across, it's going to be dividing. And so that's what's going to give us the answer for t. So t will be equal to 5,730 times the natural log of 0.91. When you enter it on the calculator, might help if you put that in parentheses, then divide it by the natural log of 0.5. And so that will give you the answer for that. So I'm going to put that on my calculator. And I will get 779.6. So since we're talking about years, let's round this to 780. Recall that, and actually, oh, okay, yes, we're using t, not x. 780. And so that will be the answer. At the time the table was found, you could assume that that amount of carbon-14 that was remaining in the table was lost, or the 9% was lost in this period of time, 780. I recalled that, in fact, let me look it up right now on my phone. And so King Arthur was, okay. he led the defense of Britain in the late 5th and early 6th century. So if the first century goes from year 0 to year 100, that means the second century is from year 101 to 200. And so the 6th century will go from 601 to 700. So I don't know. It is kind of close. Perhaps, yeah, it could have been from him. And that was actually the question here. How old is this table? So not if it was from him, but the table was 780 years old. Okay, so the last problem of this section, it deals with the application of logarithmic functions. And this is the Richter scale, which is the scale in which earthquakes are measured. And so I believe they do go from 1 to 10. And at 9.1, as you can see here, this was an underwater earthquake that caused the disastrous 2004 tsunami in Southeast Asia. It was a 9.1 on a Richter scale. So to measure this ones, people use the intensity of an earthquake, which it will be R of I, not to confuse with imaginary numbers. And that will be the output, kind of like our Y or our F of X. But in this case, we're calling it R of I. And so what that tells me is that I is the intensity, it's the independent variable, and we're using that in place of X, is the intensity of the ground motion of the earthquake. And I sub 0 is the intensity of the ground motion of a so-called zero earthquake. And that is the smallest detectable earthquake. That is what they call zero earthquake, or I sub 0. So the question here is, how did the ground motion of the tsunami compare with that of the zero earthquake? And so if we replace the output with the intensity given to us, 9.1, in fact, this I and this I sub 0. And remember, if you don't have a base, we use base 10. And I'm actually not sure if I'm doing the correct substitution, but I'm going to try. So we have here 10, the base, to the power 9.1 is equal to I divided by I sub 0. Yeah, that is correct. And so if we want to for the intensity of this earthquake, you could see here how I sub 0 is dividing So if we take that across, it's going to be multiplying. And so what this tells me is that we're going to multiply 10 to the power 9.1 times I sub 0. And so to answer this question, the intensity of that underwater earthquake with a 9.1 on a Richter scale was 10 to the power 9.1 times more intense as the intensity of an earthquake, of a 0 earthquake. What is the Richter scale intensity of an earthquake with 10 times as much ground motion as that one? And so that will be something like multiplying 10 times 10 to the power 9.1 times I sub 0. And what that will give us is we can use that rule with exponents that we have here, that states that if you multiply two variables, in this case 10, and what you do with them, you add the exponent. So that will be 10 to the power 10.1 times the intensity of a 0 earthquake. So that will be some 10 times as much ground motion. And that concludes this video.